Hello students. So here with the next video I am continuing the next concept of the chapter alternating current. Okay, so today we are going to discuss about one more new concept which is called as electrical resonance. Okay, so today we are studying about the concept of electrical resonance. Okay, so you already know how a series LCR circuit will be. Okay, we have already formed a derivation and we have obtained a expression for its impedance of series LCR circuit. You already know how that circuit will be. How the circuit will be? It will be having one inductor, it will be having a capacitor, and it will be having one resistor. LCR circuit, series LCR circuit, and that will be applied with some power source, AC source we will be having. Okay, so you have already studied about such circuits. Okay, in the a very important derivation we have done, which will give us the expression for impedance Z. The impedance Z we have already obtained. So that expression, that derivation is what? Very important. Okay, so here you already know this is one series LCR circuit. Okay, so when in this series LCR circuit the condition of electrical resonance is obtained. What is the condition of electrical resonance and when it will occur in this circuit, that I am going to tell you. Okay, so if in this series LCR circuit, in this series LCR circuit, this current shows a maximum current, means the current of this LCR circuit becomes a maximum. That is what? Current I becomes maximum if the current in this circuit, series LCR circuit, becomes maximum for a given frequency, of the source, for which the capacitive reactance, what is capacitive reactance? XC becomes equal to the inductive reactance. In this series LCR circuit, the circuit will show a maximum current. The circuit will show maximum current for a frequency at which the capacitive reactance becomes equal to the inductive reactance. Understood? Means what's happening here? In this series LCR circuit, the current is reaching the maximum value. The current is becoming maximum. But when the current is becoming maximum, when the current is able to become maximum, means here in the AC source we have to apply a particular frequency F, or you consider mu. Okay, for a particular frequency of this AC source, the current in this circuit becomes maximum. So for which frequency this will become maximum? The frequency at which the capacitive reactance becomes equal to the inductive reactance. Understood? So in this series LCR circuit, the current will become maximum for a given frequency of the AC source at which the capacitive reactance becomes equal to the inductive reactance. Understood? So how we can define a series LCR circuit? The series LCR circuit, electrical resonance is said to takes place. In a series LCR circuit, electrical resonance is said to be takes place when the circuit allows maximum current. When this circuit allows maximum current for a given frequency of the AC source, for which capacitive reactance becomes equal to the inductive reactance. Note this definition. What I am telling, electrical resonance is said to takes place in a series LCR circuit when the current of the circuit becomes maximum. Start writing the definition. I am telling what is the electrical resonance. The electrical resonance is said to takes place in a series LCR circuit when the current of the circuit become maximum for a frequency of AC source at which capacitive reactance becomes equal to the inductive reactance. Understood? So at this condition of maximum current is called as electrical resonance. Okay, so as I told you, for a particular frequency only electrical resonance is achieved in this circuit. So to that particular frequency means the frequency at which electrical resonance occurs. The frequency at which electrical resonance occurs is called as what? Resonant frequency. Is called as what? Resonant frequency. I will denote it by F or mu naught. The frequency at which electrical resonance occurs in the series LCR circuit is called as resonant frequency. Understood? So at this frequency the current in this circuit becomes maximum. Current becomes maximum means what? You already know the AC oscillations will be like this. Yes, so this is what? Amplitude. This is amplitude. I had told you already. I had told the example of simple pendulum also. Maximum amplitude. Okay, so if the current of this circuit becomes maximum, the amplitude of the oscillations also will be maximum. So at resonant frequency the amplitudes will be very high. Understood? So at resonant frequency in this circuit electrical resonance is achieved. So at that time how the amplitudes of the AC will be? They will be very high, means maximum. The amplitude of the AC oscillations is maximum at the resonant frequency because of the achievement of electrical resonance. Understood? So this is what exactly is electrical resonance condition taking place. Okay, so what if the current is maximum? What will be the value for that current? What will be the value for that maximum current? You already know current is nothing but what? I is equal to V by Z. I is equal to V by Z. So you already got an expression for Z. Got an expression for impedance, that is what? R square plus XL minus XC whole square. XL minus XC whole square. This is the expression you got for Z. So the current of the LC circuit will be this much, V divided by R square plus XL minus XC whole square. Okay, so the current can become maximum only if Z is minimum. Yes or no? If Z is minimum, by this expression you can understand that I will be maximum only if this Z will be minimum. So how this Z can become minimum? How this equation can become minimum? You already know the electrical resonance takes place when XL is equal to XC. Okay, so in this expression you add XL are equal to XL and XC are equal to each other. So this whole term will get cancelled. So what you are remaining with? You remain with I is equal to V by R. Yes. So at the particular frequency the current amplitude in the LCR circuit becomes maximum. And when the current becomes maximum, the Z will always be minimum. Z becomes equal to R, na? Z becomes equal to R. So if it becomes minimum, if this term becomes minimum, current will always be at the high rate. Current will always be maximum. Okay, and the frequency mu naught or F is called as what? Resonant frequency. And this whole phenomena of getting maximum current in the series LCR circuit is called as what? Electrical resonance. Understood? The phenomena in which the current of the series LCR circuit becomes maximum for resonant frequency when the inductive reactance becomes equal to the capacitive reactance. This is what is called as electrical resonance. This is what is called as what? Electrical resonance. Okay, so now you understood about the concept of electrical resonance. What is the phenomena of electrical resonance? You understood. Okay, so there you got one term which was called as what? Resonant frequency. What is that? Resonant frequency mu naught. Okay, so now let obtain an expression for this resonant frequency. Means let get a formula for this resonance frequency. So how to obtain the formula for resonant frequency? You already know, in the condition of electrical resonance, in the phenomenon of electrical resonance, we got a condition. What is that condition? XL should be equal to XC. The inductive reactance should be equal to capacitive reactance. Okay, that means what? XL is nothing but L into omega naught, and XC is nothing but C into omega naught. Understood? This only. So both the omega naughts I am sending to one side. So omega naught square, this omega here, omega naught, and L will come downside, 1 by L into C. Omega naught square is equal to what? 1 by L into C. Okay. So what omega naught will give now? Omega naught is nothing but what? 1 by square root of L into C. Okay, but you already know the angular frequency omega is nothing but 2 pi f. I always told you about this. Omega is nothing but omega is equal to 2 pi f. I always keep on telling this. Omega is equal to 2 pi f. So what omega not equal to now? Omega not equal to 2 pi f naught. That means what? Omega naught is equal to 2 pi mu naught, you can consider, is equal to 2 pi mu naught equal to 1 by square root of L into C. So what mu naught will give now? Mu naught is nothing but what now? 1 by 2 pi square root of L into C. So this is expression for resonant frequency. The frequency at which current in the series LCR circuit becomes maximum for XL equal to XC. Understood? This is about what? Resonant frequency. Okay, and this resonant frequency is independent of R. This resonance frequency is what? Independent of resistance of the circuit. It will not depend on the resistance of the circuit. I will tell you this statement. I will explain this statement by using a graphical representation. Okay, so in the y-axis I am showing the variations of current, and in the x-axis I am showing how the omega or omega naught it is, because it is resonant angular frequency. Okay, and this omega is resonant, this mu naught is resonant frequency. Okay, I told you mu naught is independent of R. Okay, so I am explaining this, I am justifying my statement by showing a variation of current and omega naught. Okay, so when we are getting the readings, okay, we'll get some curve like structures, like we'll get a curve like this, again we'll get a curve like this, again we'll get a curve like this, Okay, the variations of I and omega naught will give you such structures. Okay, so this first curve, the first curve is when we'll get resistance R3, you consider. Second is for the resistant R2. First is for the resistance R1. And what the interesting thing I am going to tell you is R3 is greater than R2 and R2 is greater than R1. So R1 is the smallest, R2 is bigger than R1 and R3 is bigger than all. Okay, so for less value of resistance, for less value of resistance, less value R3, we will get a small curve. We'll get a small curve with no any sharpness. You see, in this curve we don't have sharpness here. Sharpness means what? Like this is sharp, this is what? Peak. Okay, like this here we don't have any sharpness or we don't have any peak here. Okay, so as the resistance decreases, R3 is bigger, R2 is low. As the resistance decreases, we'll get a slight sharpness. Okay, so for a less value of resistance, for a very less value of resistance, we will get a highest sharpness in the curve. Understood? That means what? The sharpness of the resonance curve, the sharpness of the resonance curve increases with decrease in the R. Understood? Sharpness of the resonance curve increases with decrease in the R. Understood? R3 is very much bigger but sharpness is less. R1 is less but sharpness is high. Understood? This is how the current can become maximum at the current can become maximum in the series LCR circuit at the resonance frequency. So here see, R is very less, R1 is very less. So at the very less value of the resistance, we are getting a sharp curve. Sharp curve means what? High current. I is maximum. The maximum current, the sharp curve will shows us the maximum current, and the sharp curve is obtained only at less value of the resistance. Understood? So as the resistance decreases, sharpness of the curve increases. As the resistance decreases, the maximum current increases. Understood? This is the phenomena which takes place actually in the electrical resonance. Understood? This is about electrical resonance and resonant frequency. This is easy to understand. Okay, so one more doubt I am having. I'm having one doubt. Okay, so there I had read a statement. I read a statement in the book right now that the resonance, the electrical resonance cannot be obtained. The electrical resonance is not obtained in a RL or RC circuit. They have given a statement in the book that electrical resonance is not obtained in RL or RC circuit. They told electrical resonance can obtain only in the LC circuit. Only in the LC circuit, not in RL and RC circuit. Why is it so? I am also not understanding. Why is it so? Okay, I am giving you a small thing to think and answer to this question in the comment box. As you watch this video on YouTube, you know how to write the comments over there. Okay, so I want the answer from every one of you for this question. What is my question? In book they have written electrical resonance cannot takes place in RL or RC circuit, but electrical resonance takes place in only in LC circuit. Why is it so? I want answer. Okay, if you can answer for this question, I can think that you have understood the concept of electrical resonance. Okay, in the comment box I am waiting for your answers. Okay, so next concept, moving on to the next thing is, so I told you about the sharpness of the curve. I told you about the sharpness of the curve, how we are getting the sharpness for the curve of variations of I and omega. Okay, so to understand about the sharpness of the curve, one quantitative thing we have, that is called as what? Q factor. That is called as what? Q factor. So what is the Q factor? The Q factor will give us the Q factor will give us about the information about sharpness of the resonance curve. What is the sharpness of resonance curve? This is the sharpness of the resonance curve. Yes, so the quality factor will give us the information about sharpness of the resonance curve. Okay, so Q factor means what? Quality factor. So how can we define this quality factor? What is the definition of this quality factor? Means the Q factor or the quality factor of the LCR circuit can be defined as, this is denoted by Q, and it can be defined as the ratio of voltage developed across the inductor. The ratio of voltage developed across the inductor, that is VL, to the voltage applied to the circuit. Understood? The Q factor can be defined as the ratio of voltage developed across the inductor to the voltage applied to the circuit. Or also we can write it one more definition. The Q factor or quality factor of the LCR circuit is nothing but it is the ratio of the voltage developed across the capacitor. It is the voltage developed across the capacitor to voltage across a resistance. Understood? We can write the two definitions. What? The Q factor or quality factor of LCR circuit is defined as the voltage developed across the inductor to the voltage applied to the circuit. Next, voltage developed across the capacitor to the voltage developed in the resistor. Understood? So these are the two definitions. So how can we, again we can get the simplified expression. As you get the expression for F or mu naught, you can also get the expression for Q also. What is the expression for Q? You can obtain now. Now you already know how we can write VL. How can I write VL? VL is nothing but I into XL. And how I can write VC? I into XC. And what is the voltage developed across the circuit? V is I into R, and here also V is I into R. Okay, so what you are getting here? I get cancels. XL divided by R. What is XL? XL is nothing but L into omega naught divided by R. So now again simplify. What is the value for omega naught? See here. In omega naught, here we have got 1 by square root of LC. So omega naught is 1 by square root of LC. So Q is equal to L into 1 by square root of L into C into divided by R. Okay. So again here we can cancel up R. Q cancel up L. L is nothing but root L into root L we can write na. Root L into root L is L only. Root L into root L is L only, divided by, in the denominator we have R root L root C into root L. Root L get cancels. So Q is equal to square root of root L divided by R into square root of root C. Understanding na? So Q is equal to 1 by R into square root of L by C. Understood? This is the expression of quality factor. Okay, so same, by this also you can get the same thing, you can get the same last answer. So can you try? Okay, I will solve here, but before that you just try it to get the, because I have given. So further what you have to do, at the place of xc you have to put 1 by c omega naught. Here we have xl, at the place of xl we have written l into omega naught. So at the place of x you have to write 1 by c omega naught. Okay, so by putting that you try to solve and try to get the last answer. I will solve, no problem, but you only try to solve it first before watching my explanation, my derivation. You try to solve by yourself. Okay, so q is equal to I get cancels, 1 by c omega naught into r, and you already know the value for omega naught. What is that? 1 by omega naught is equal to 1 by square root of L into C. So omega naught is already in the denominator, so I will write L by C here. So C into R. Okay, so this C you can split. L and C you have here. C you can split as root C into R. So here you have root L, root C, root C, root C, R. C get cancels. So again Q is equal to 1 by R square root of L into C. The same definition, same answer you will get. This is about a quality factor. Understood? So this quality factor, what is the significance of the quality factor? Quality factor will give us the information about sharpness of the resonance curve. Quality factor will give us the information about sharpness of the resonance curve. Okay, and also we have another expression for the quality factor. Okay, so and while dealing with the concept of Q factor, we'll come across one more important thing, one more very essential thing, that is bandwidth. Okay, so what is that? What is bandwidth? Okay, so now you know, at the resonant frequency or at the resonant angular frequency we will get the highest current. Okay, I'll try to show that like. Okay, so here I am showing the current and here we are showing the omega naught. Okay, so we will get a highly sharped curve. We will get a highly sharped curve at the angular frequency omega naught. Yes, the highest curve is obtained only at what? The resonant frequency or resonant angular frequency. So when the resonant angular frequency is giving you highest curve, that means what? You are getting a maximum current, that is I naught. You are getting a maximum current I naught. Yes, is it being blur? Okay, it's being blur, I think. Okay, no problem. Okay, so here, to explain the concept of bandwidth, what I am doing means I am considering two angular frequencies, omega 1 and omega 2. Two angular frequencies below and above the resonant angular frequency. Means what? See here, two angular frequencies, omega 1 and omega 2, below the angular frequency and above the angular frequency. So at omega and omega 2, whatever the current we will obtain, that is 1 by root 2 times of the I naught. So what I am doing, try to understand. At omega naught we are getting the current I naught, maximum current, but at omega 1 and omega 2, below and above the omega naught, omega 1 and omega 2 are there. So at that time 1 by root 2 times of I naught we are getting. So at omega 1 and omega 2, I naught divided by root 2 is I am taking. Understood about this graph? Okay, so let consider this omega 1 is what? This omega 1 is this omega 1 omega 1 is below the omega naught. This omega 1 is below the omega naught and omega 2 is above the omega naught. Hence, I can write omega 1 is equal to omega naught plus del omega, because this is lesser. Omega 1 is small than omega 2. Omega 1 is small than omega naught. So, for omega naught, we have to add something. Next, omega 2 is equal to omega naught minus del omega. So for the above and below frequencies of angular frequencies, we are getting omega 1 and omega 2. Anyone you can consider. Omega 1 you can consider greater than omega naught. Yes, omega 1 is greater than omega naught. Sorry, I told it is smaller, but actually I am considering omega 1 as greater than omega naught. That's why we are adding some extra component. And omega 2 is less than omega naught. Hence, we are subtracting some extra component. Understood? So now, taking the difference in omega 1 minus omega 2. Take the difference. Omega 1 minus omega 2. Difference means what is this? Subtraction. Okay, so omega naught plus del omega minus omega naught minus del omega. Okay, so omega naught plus del omega minus omega naught plus del omega. Plus omega naught minus omega naught get cancels. So the difference in omega 1 minus omega 2 is 2 del omega. And this is called as bandwidth of the circuit. Understood? The difference in the frequencies omega 1 minus omega 2 is called as bandwidth of the circuit, and the quantity, the ratio of omega naught to 2 del omega is also called as a quality factor. Means the expression for quality factor in terms of bandwidth I am telling. Expression for quality factor in terms of the bandwidth is the ratio of omega naught to the 2 del omega. Understood? So this is about what? Quality factor with respect to the bandwidth. Okay, and also the quality factor of the circuit. The important thing you have to keep in mind that the quality factor will give the information of sharpness of the resonance, or the quality factor or the Q factor will measure the sharpness of the resonance of the series LCR circuit. Understood? This is all about what? Quality factor and bandwidth. Okay. So one last thing I am telling. Power in an AC circuit. One more thing is power in AC circuit. Power dissipated in an AC circuit that we have to think. So it is very easy thing or very easy thing to remember. Power dissipated in an AC circuit is nothing but the product of RMS value of voltage. I hope you know RMS value, peak value, instantaneous value and all. We have discussed it at the initial classes only. Okay. So power dissipated in an AC circuit is nothing but the product of RMS value of voltage and the component of current with RMS voltage. Understood? So power dissipated in an AC circuit is the product of RMS value of the voltage and the component of current in phase. Component of current in phase means we are considering a phase here cos pi. We don't have any special definition. Whatever the formula we are having, for that only I am framing the definition. So power in an AC circuit or power dissipated in an AC circuit can be defined as the product of RMS value of voltage and the component of current in phase with RMS voltage. Understood? The product of RMS value of voltage and component of current in phase with the RMS voltage. This is what power dissipated. You know Vrms and Irms are the what? Root mean square values of voltage and current. And you know this already. And this cos pi is known as what? It is power factor. Cos pi is known as what? It is power factor. Understood? Hence, the power dissipated in an AC circuit is nothing but the product of RMS value of voltage and the component of current in phase with RMS voltage, where Vrms and Irms are the RMS voltage and currents, and cos pi is known as the power factor. Okay, but here one thing is the P, whatever P we are having, that P is called as what? True power. P is called as what? True power. P is called as true power, and the product and the products Vrms and Irms. This Vrms and Irms is called as what? Apparent power or virtual power. Virtual means what? Imaginary. They are not true. They are imaginary. They are called as what? Virtual power. Okay. So this is about what? What is the power dissipated in an AC source. Okay. So related to this thing, we can discuss some special cases. We can discuss some special cases. What means how means if the AC circuit is having only resistor, if the circuit is having only resistor, means in that circuit only we are having resistor, so at that time what will be the power? What will be the power? So how can we think of this? We have this formula, P is equal to Vrms into Irms into cos pi. Okay, so if in this circuit only resistance is there, so pi is equal to 0. The angle pi is equal to 0. So cos 0 is 1. Cos 0 is 1. So what P is equal to? Vrms into Irms. Understood? So when in the circuit only if you have resistor, the true power becomes equal to the virtual or apparent power. This is the first case. Second, if in the circuit we are having only inductor, we are having a pure inductor in that circuit, so at that time the angle between voltage and current, or the pi is what? Pi by 2. So pi is pi by 2, cos pi by 2 is 0. So whole term becomes 0. So if we are having pure inductor, if you are having pure inductor in the circuit, the power loss takes place in the circuit is 0. Understood? Here power loss is equal to the product of RMS voltage and RMS current, means true power is equal to virtual power, but in the pure inductive circuit we have P is equal to 0. And what happens in the pure capacitive circuit? There also we are having pi is equal to pi by 2, hence P is equal to 0. These are some extra things you can understand about the concept of power. And to understand more about this power factor, if I want to say something about this power factor, so this power factor, how can we define this power factor? you know p is equal to IRMS into VRMS into cos pi. So how can we define this cos pi? This is the formula we are having. So cos pi is nothing but what? P divided by VRMS into IRMS. Yes, so can we define this power factor as the ratio of true power to virtual power? Yes, the power factor is nothing but what? Ratio of true power to virtual power or apparent power in an AC circuit. Understood? So you can also write it as P divided by P RMS. So this is what the definition and formula for the power factor. Okay, and this power factor is always positive, and always less than 1. Always it is 1 or less than 1. Always it is 1 or less than 1, not more than 1. It will never be more than 1. Okay, so and already you got the values here for a circuit having pure resistor. For a circuit having pure resistor, what is the power factor? Cos pi is equal to 1. Yes, for a circuit having pure inductor or pure capacitor, you already made here. We are having cos pi is 0. So, and for a RC circuit, we have cos pi as R divided by square root of R square plus 1 divided by omega square plus C square. This is already given. And similarly, you can write for the LR circuit. LR circuit means what happens here? At the place of C, it will having L. And totally for the LCR circuit, what we can write? Totally for the LCR circuit, we can write the power factor as R cos pi is equal to R divided by square root of R square plus LW minus 1 by C omega whole square. That you already know. Okay, so this is about the power factor. This is about the power factor and power of an AC circuit. Okay, so it's already for time has been finished. So today we learned about what all the things we learned about today. We learned about electrical resonance, all the things we have studied here, and a resonant frequency. What is the expression for resonant frequency we have studied. And main thing, I have given you a mind storming thing. Okay, I am not giving any homework to you. I just given a little work to your mind to think. Okay, if you can answer, comment me in the comment box. Okay, and then we studied about Q factor. And the bandwidth, Q factor in terms of bandwidth, and the power in an AC circuit, and power factor cos pi. Okay, so in this alternating current, At the last, we are remaining with only concept transformers. Okay, so in the next class we will discuss about transformers, and after that I'll solve some problems and I will give you the notes, and we will end up successfully with the chapter alternating current. Okay, today's class I will finish up here only. Take care. Bye bye.